Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video we will talk about work, heat transfer, enthalpy, and entropy of gases. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Let's start with the basics. As we said before, thermodynamics is a branch of physics that deals with how energy moves and changes form, especially in the form of heat and work. In other words, it's the study of how energy flows within physical systems. Unlike microscopic physics, which looks at the behavior of individual molecules or atoms, thermodynamics focuses on the large-scale behavior of matter, the kind we can actually observe and measure in experiments. As aerodynamicists or engineers, thermodynamics becomes especially important when we study propulsion systems, like jet engines, rockets, or turbines, because these systems rely on energy transformation to generate thrust and motion. Understanding thermodynamics helps us figure out how efficiently an engine can convert fuel into useful mechanical work. Now, one of the most important ideas in thermodynamics is the first law of thermodynamics. This law tells us that energy can never be created or destroyed. It can only be transformed from one form to another. So when heat enters or leaves a system, that energy either changes the internal energy of the system or is used to perform work. In simpler terms, the energy you put in always has to show up somewhere. Nothing is ever lost, just transformed. Work. Let's pause for a moment and talk about what we really mean by work. In everyday life, we think of work as any physical effort, like lifting a box, pedaling a bike, or even running. But in science, we define work much more precisely. Work is the product of a force acting over a distance. Imagine an aircraft that starts moving at time zero under the thrust force produced by its engines. As the engines continue to apply a constant force F, the aircraft accelerates and moves forward through a distance s. The total work done on the aircraft during this time is given by the formula. Work equals force multiplied by distance. Here, the force is the thrust from the engines, and the distance is how far the aircraft travels from the starting moment, time equals 0, to some later time. The standard unit of work in the metric system is the joule, which equals 1 Newton of force acting through 1 meter of distance. In the English system, the equivalent unit is the foot-pound. Now, that's a nice simple example, but real life is rarely that neat. In most real situations, the force acting on an object doesn't stay constant. It can change in size and even direction. For example, as an airplane climbs, turns, or descends, the forces acting on it are constantly shifting. When that happens, the total work done is calculated by integrating, or summing up, the components of the force that act in the same direction as the object's motion. Only that part of the force that's aligned with the motion actually performs work. In general, the total work can be written as work equals the sum of the force multiplied by the cosine of the angle between the force and the direction of motion, phi, multiplied by each small change in distance. Here, phi is the angle between the direction of the force and the direction of the displacement. Here's an interesting thought experiment. Consider an airplane cruising steadily at altitude. The lift force is acting upward, while the airplane is moving forward. Since lift is perpendicular to the motion, it doesn't actually do any work, it just keeps the airplane in the air. The thrust, however, is aligned with the direction of motion, so that's what performs the work to keep the plane moving forward against drag. Let's take another example. Imagine the aircraft sitting on the runway with its brakes fully applied, engines running at full throttle. Even though the engines are producing a large amount of thrust, the plane isn't moving, the displacement is zero. And because there's no displacement, the engines are doing no mechanical work on the aircraft. All that energy is simply turning into heat, vibration, and sound instead of motion. Work done by a gas. So far, we've talked about work being done on solid objects. But in thermodynamics, we also deal with gases, and the concept of work looks a little different there. For gases, work is done whenever the volume changes while under pressure. Think about it this way. Pressure represents a force per unit area, and volume changes when the boundaries of the gas move, like a piston sliding in a cylinder. If the gas expands, it pushes the piston outward, doing work on the surroundings. If it is compressed, work is done on the gas. This idea is not just theoretical, it's the principle behind engines and turbines all around us. The state of a gas is determined by measurable properties such as pressure, temperature, and the volume it occupies. These properties can change, resulting in a new state for the gas. For example, imagine a gas confined in a jar. In one state, the gas may have high pressure and occupy a small volume, which we call state 1. In another state, it may have lower pressure and a larger volume, known as state 2. We can represent these states visually on a graph of pressure versus volume. To move the gas from state 1 to state 2, we can change the conditions in the jar by heating the gas, physically moving the piston to adjust the volume, or altering the pressure by adding or removing weights. Each method changes the state differently, and thermodynamics allows us to calculate how much work is done or how much heat is added or removed during these changes. There are several ways to change the state of a gas, and the path taken matters. For instance, if we gradually remove weights from the piston, allowing the gas to expand and the pressure to decrease naturally according to Boyle's law, the path on the pressure-volume graph is curved. The work done by the gas in this process corresponds to the area under this curve. Alternatively, we could heat the gas at constant pressure, moving first from state 1 to an intermediate state, A, which has the same pressure but a larger volume. Then, by adjusting the pressure at constant volume, we reach state 2. In this case, the work done corresponds to a different area under the graph. These examples show that the work done by a gas depends not only on its initial and final states, but also on the specific process used to change the state. Scientists define work as the product of a force acting through a distance. For gases, work occurs when the volume changes under pressure. Pressure acts as a force per unit area, and when the gas expands or contracts, the moving boundary, such as a piston, translates this force into work. A quick units check shows that pressure, force per unit area, multiplied by volume results in units of force times distance, which are the units of work, joules or foot-pounds. When both pressure and volume change during a process, the work is expressed mathematically as an integral. The work done by a gas is equal to the integral of the pressure with respect to the change in volume. Or, more naturally, work is calculated by summing up the small amounts of pressure multiplied by the corresponding small changes in volume as the gas changes state. On a pressure-volume graph, the work done by the gas corresponds to the area under the curve connecting the initial and final states. We see these principles in action every day. Consider the cylinder of a car engine. When the air-fuel mixture burns, it produces hot gases that expand and push the piston downward. This expansion performs work which is transferred through the crankshaft to generate mechanical motion, ultimately moving the car. In a jet engine, high-pressure gases produced by combustion expand rapidly and rush out of the exhaust, doing work on turbine blades and producing the thrust that propels the aircraft forward. Even something as simple as a refrigerator relies on thermodynamic work, as a gas is compressed and expanded in the cooling cycle to transfer heat away from the interior. As you can see, thermodynamics is not just an abstract or theoretical subject. It is the science that explains how energy powers the world around us, from the engine in your car, to the refrigerator in your kitchen, to the jet that carries you across the globe. Every time energy changes form, whether fuel turning into motion or heat being converted into work, thermodynamics is at play. Enthalpy. As we know, the state of a gas is defined by several properties, including its temperature, pressure, and the volume it occupies. From our study of the first law of thermodynamics, we know that the internal energy of a gas is also a state variable. This means that internal energy depends only on the current state of the gas, not on the process that led the gas to that state. In thermodynamics, we can also define additional state variables that are combinations of existing variables, and these often simplify the analysis of a system. One particularly useful variable for gases is enthalpy, denoted as H. Enthalpy is defined as the sum of the internal energy, E plus the product of pressure P, and volume V. Enthalpy is equal to the internal energy plus the product of pressure and volume. Enthalpy can also be expressed as a specific or intensive variable by dividing it by the mass of the gas. In propulsion and engine analysis, engineers often work with specific enthalpy rather than total enthalpy because it is more convenient for calculations involving flow and energy per unit mass. To understand the practical use of enthalpy, let's revisit the first law of thermodynamics for a gas. For a system experiencing heat transfer Q and doing work W, the change in internal energy is equal to the heat added to the system minus the work done by the system. The change in internal energy from state 1 to state 2 is equal to the heat added to the system minus the work done by the system. In this equation, both work and heat transfer generally depend on the process used to change the state of the gas. However, in the special case of a constant pressure process, the work done by the gas can be expressed simply as the pressure times the change in volume. Work is equal to the constant pressure multiplied by the change in volume from state 1 to state 2. Substituting this into the first law equation gives the change in internal energy from state 1 to state 2 is equal to the heat added to the system minus the pressure multiplied by the change in volume. We can then rearrange this equation to group together the properties at the final state 2 and the initial state 1. The sum of internal energy and the product of pressure and volume at state 2 minus the sum of internal energy and the product of pressure and volume at state 1 is equal to the heat added to the system. From our definition of enthalpy, the sum of internal energy and the product of pressure and volume can be replaced by the enthalpy, so the equation becomes much simpler. The enthalpy at state 2 minus the enthalpy at state 1 is equal to the heat added to the system. From our definition of heat transfer, we can represent the heat added by some heat capacity coefficient at constant pressure multiplied by the change in temperature at constant pressure. The change in enthalpy at constant pressure is equal to the heat capacity at constant pressure multiplied by the change in temperature at constant pressure. We have enclosed the terms of the equation with a p subscript to remind ourselves that this is only true for a constant pressure process. At the bottom of the slide, we have divided by the mass of gas to produce the specific enthalpy equation version. The specific heat capacity at constant pressure is related to the universal gas constant of the equation of state. This final form is highly practical. It allows us to calculate the specific enthalpy for a gas given its temperature and is especially useful in propulsion systems. For instance, enthalpy is used to determine the work done on the flow by a compressor or the work that can be extracted from a power turbine. Essentially, it gives us a direct way to link thermal energy in the gas to the mechanical work that can be produced, which is fundamental in understanding engines, turbines, and other thermodynamic machines. Entropy of a gas. The first law of thermodynamics indicates that the total energy of a system is conserved. This includes the potential and kinetic energy, the work done by the system, and the transfer of heat through the system. The second law of thermodynamics states that, while many physical processes satisfy the first law, the only processes that naturally occur are those for which the entropy of the system either remains constant or increases. Entropy, like temperature and pressure, can be explained on both a macro scale and a micro scale. Since thermodynamics deals primarily with the macro scale, here entropy is defined as the heat transfer into the system divided by the temperature. S is entropy, P is pressure, T is temperature, and V is the volume of the gas. H is enthalpy, E is internal energy, Q is transfer. R is the gas constant, Cp is the heat capacity at constant pressure, Cv is the heat capacity at constant volume. D represents a differential change of a variable, while delta represents a finite or large change. Equation 1, second law of thermodynamics in finite form. The change in entropy is equal to the heat transferred divided by the temperature. During a thermodynamic process, the temperature of an object changes as heat is added or removed. A more precise definition of entropy uses the differential form, which accounts for varying temperatures. Equation 2, differential form of the second law. The differential change in entropy equals the differential heat transfer divided by the temperature. For gases, the change in entropy can be evaluated in two ways, using internal energy or using enthalpy. Entropy change in terms of internal energy. The first law of thermodynamics can be expressed as Equation 3. The differential heat transfer equals the differential internal energy plus pressure multiplied by the differential volume. Using the ideal gas equation. Equation 4. Pressure multiplied by volume equals the gas constant times the temperature. Substituting the ideal gas law into equation 3 gives equation 5. Differential heat transfer equals differential internal energy plus the gas constant times temperature multiplied by differential volume divided by volume. For a constant volume process, the differential heat transfer equals Cv times the differential temperature. Equation 6. Differential internal energy equals differential heat transfer equals Cv times differential temperature. More generally, in equation 7. Differential heat transfer equals CV times differential temperature plus R times temperature times differential volume divided by volume. Substituting into the differential form of the second law gives equation 8. Differential entropy equals CV times differential temperature divided by temperature plus R times differential volume divided by volume. Integrating from state 1 to state 2 gives equation 9. Entropy change equals CV times the natural logarithm of T2 over T1 plus R times the natural logarithm of V2 over V1. Entropy change in terms of enthalpy. The first law in terms of enthalpy gives equation 10. Differential heat transfer equals differential enthalpy minus volume multiplied by differential pressure. Substituting volume from the ideal gas law gives equation 11. Differential heat transfer equals differential enthalpy minus R times temperature multiplied by differential pressure divided by pressure. For a constant pressure process, the second term is 0, and the differential enthalpy equals the differential heat transfer. Equation 12. Differential enthalpy equals differential heat transfer equals Cp times differential temperature. More generally in equation 13. Differential heat transfer equals Cp times differential temperature minus R times temperature multiplied by differential pressure divided by pressure. Substituting into the differential form of the second law gives equation 14. Differential entropy equals Cp times differential temperature divided by temperature minus R times differential pressure divided by pressure. Integrating from state 1 to state 2 gives equation 15. Entropy change equals Cp times the natural logarithm of T2 over T1 minus R times the natural logarithm of P2 over P1. Specific forms of equation 9 and equation 15 can be developed by dividing by the mass to obtain the specific heat capacities and specific volumes, which are commonly used in practical thermodynamics and propulsion analysis. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Which of the following best describes the first law of thermodynamics? The correct answer is energy cannot be created or destroyed, only transformed. Question 2. In thermodynamics, how is work done by a gas represented? The correct answer is pressure multiplied by the change in volume. Question 3. Which statement about entropy is correct? The correct answer is entropy always remains constant or increases in natural processes. Question 4. How is enthalpy H defined? The correct answer is internal energy plus pressure times volume. Question 5. For an airplane cruising steadily, which force does mechanical work to maintain forward motion? The correct answer is thrust. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about Introduction to Propulsion. See you in the next video. Bye.